Hello everyone. Today we're going to learn about kinetic molecular theory so that we can predict the behaviors of gases. A quick review. Particles are always in motion. All particles, electrons, atoms, molecules, etc. are always moving. Kinetic energy is the energy that is associated with movement. As the speed of particles increases, their kinetic energy will also increase. Generally speaking, when we discuss the states of matter, the lowest kinetic energy is usually found in the solid state, while the highest kinetic energy usually occurs in the gaseous state. Temperature is a measure of average kinetic energy. The temperature of a sample is directly related to how quickly the individual particles are moving. So therefore, at a lower temperature, I would expect to be in a solid state, and at a higher temperature, I would expect to be in a gaseous state. An ideal gas is a gas whose behavior is predicted according to what we call kinetic molecular theory, or KMT. These are the behaviors we expect to take place when gases behave in a manner that is predictable and considered ideal. There are 5 key assumptions to kinetic molecular theory that help us predict how a gas should behave. The first of these assumptions is that the gas particles themselves have almost no volume compared to the total volume of the sample they occupy. So for example, if we consider a gas particle trapped inside a balloon, that individual particle is so small compared to the balloon itself. Therefore, we treat the gases as almost essentially empty space. We take the volume of the shape that the sample occupies rather than looking at the volume of individual particles when we discuss volume. Assumption number 2. The gas particles will experience no attractive or repulsive forces while they are in the gas state. This means that intermolecular forces will not play a role in the gas state, unlike in the solid and liquid states. The gas particles are therefore free to move independently and randomly. Speaking of, assumption number 3 is that the particles are in continuous random motion, also known as Brownian motion. The gas particles will constantly be moving, and it will be completely random, which is helped by the fact that there are supposedly no intermolecular forces present. If particles happen to collide, assumption number 4 says that all collisions between the gas particles will be elastic. An elastic collision is one in which no kinetic energy is lost or converted into some new form of energy. This does not mean that all particles have their same speed. It just means that the total kinetic energy of the two particles is the same. One of them could transfer some of their kinetic energy to the other, but the total kinetic energy remains the same. Our 5th and final assumption is that the average kinetic energy of all gases is the same at a given temperature, regardless of what kind of gases they are. So if I have a sample of nitrogen gas and a sample of oxygen gas, both at 25 degrees Celsius, then their average kinetic energy is the same, despite the fact that oxygen and nitrogen are not the same atoms or molecules. Please note, this is specifically talking about kinetic energy, not speed. Kinetic energy is proportional to both speed and mass. This does mean that speed is going to be different at different temperatures. Something that is larger will on average move a little bit slower, even though they still have the same average kinetic energy. These assumptions are important because the microscopic properties of gases have an impact on what their macroscopic properties will act like. 3 of the macroscopic properties we want to look at in detail are temperature, pressure, and volume. Temperature is a measure of the average kinetic energy of a sample. As particles move faster on average, they will move to a higher temperature. Please note it does say on average. There will always be those who are below or above the average. Appropriate units for temperature include Fahrenheit, Celsius, and Kelvin. Because we will be in a chemistry class, we will be using Kelvin, or the absolute temperature unit. That way we avoid having negative temperatures. Volume is the amount of space that something occupies. For a gas, since we are making the assumption that the particles themselves have next to no volume, we will focus on the volume of the container they occupy, such as a balloon or a box. Appropriate units for volume could include liters, milliliters, centimeters cubed, feet cubed, and so on. For this, we will use liters as an appropriate unit. Pressure is a measure of force applied over an area. For example, there is a lot of pressure on your body as you stand upright, and that pressure is on your feet, but then when you sit down, your weight is now distributed across a different area, decreasing the pressure. When we deal with gases, the force in question is the force that is exerted when particles collide with their container and or with each other. And so it is the forces being applied over the area in question. There are many appropriate units for pressure, including atmospheres, pascals, millimeters of mercury, bars, torr, pounds per square inch, and more. We will most often use atmospheres, although we will be making use of all of these different units. So, these three macroscopic properties, temperature, volume, and pressure, have important mathematical relationships that exist between them, and these relationships are caused by the behaviors of the gases at the microscopic level. The mathematical relationships of the three are expressed in what we call the gas laws. Please watch our future videos to learn more about gas laws.